have a lower limit. We try to find, so the answer for that, because it's indefinite, so the answer is a family of functions. So we add C to it. In the end, we get a function, a family of functions. It depends on the value of C. So talking about antiderivative skill, we have antiderivative, we have a power rule for antiderivative. If the integrand we can write as a power like, so we can apply power rule. Power rule is the same, power rule for antiderivative. Add 1 to the exponent, then divided by the new exponent. Or we'll have an antiderivative rule for the trig functions, right? Okay, so today, right, let's talk about the fundamental theorem of calculus. Let's see this one. So let's understand the notation of this. So let's look at the right-hand side. The right-hand side is saying the integral is from a to x, right? Looks like we have a definite integral. Looks like we have a lower limit, a represents a number. We have an upper limit, however, upper limit is not variable, x. It's not variable x. So this means the upper limit is undefined yet. It's not defined yet. It's not x, it's a variable. But the lower limit a is a number. Okay, so then the integrand is f of t, and the integral is with respect of t, dt. So the integral dt, that's a pair. The dt, that means we have this, look at this picture. So we're cutting, so this is the t-axis. This is the t-axis. So where is x? And x is somewhere from a to b, is in between, x is in between of a to b. So x is a value somewhere. X is not variable. We don't know what x is. All right, and you know, we call this g of x. All right, so give this a name. The right hand side will give a name. We call it g of x. So this gives us a function. All right, g of x. Basically, look at the picture here. So the area here is it's not function, right? Depends on the x value. Depends on the x value. Okay. Let's see example 1. If f is a function whose graph is shown in this here, and g of x equals to this integral from 0 up to x. So from 0 up to x. X can be 1, 2, 3, 4, right? So we call g of x the integral from 0 up to x ft dt. So what do we want to do? We want to find the values of g of 0, g of 1, g of 2, g of 3, g of 4, g of 5. Right? We want to find the area from 0 up to 1, from 0 up to 2, from 0 up to 4, from 0 up to 5. Okay, so let's see. So so g of 0, that means x equals 0. So we substitute x into 0. So if the upper limit and lower limit are the same point, we see the area is 0 because it's one dimension, right? It's a line or it's a point. And mathematically, we don't think a one dimension quantity has area. So that's 0. Then now let's see g of 1. G of 1, we see it's 1 here. We have area from 0 to 1, right? we have this triangle. We have 1 times 2 divided by 2, which is 1. Right? Let's see. So g of 1, we substitute x into 1. So from 0 to 1, f of t, we just look at the picture, right? Because we don't know what f of t is. We won't be able to antiderivative, but we can get from this picture. Right? We have 1. So we look at this triangle. The base is 1. The height is 2. So 1 times 2 is 2. Then divided by 2, we get this area is 1. So g of 1 is 1. Well, let's see g of 2. G of 2, we see the figure is this triangle plus this rectangle, right? So we split into 2 integrals. So 0 to 2, we split from 0 to 1 and 1 to 2. 0 to 1, we already know the area is 1. From 1 to 2, we see that's a rectangle. It's 1 times 2. So add together, we get 3. Oh, look picture here, down here. So g of 1 is 1. G of 0 is this point, 0. G of 2 is 3. How do we find the g of 3? So g of 3, we also can split, right? It's a g of 2 plus from 2 to 3. So I have this part. G of 2. So the textbook saying estimate. Okay, estimated to be 1.3. That's 4.3 in total. Similarly, to estimate for g of 4, right? G of 4 seems like this upper part, right? Cancel out this lower part, so get back to 3. Right? Or g of 5. G of 5 will have this double, so the down here, so 2 of 1.3, but be negative, so that's negative 2.6. Then minus 1.3. So in the end, we have 3 minus 1.3, which is 1.7. That's the use graph, right? That's the use graph to understand this notation. G of x equals to the integral from one point up to a variable. Okay, depends on the value of the variable. So we have different areas. So this example is to helping us to understand this equation. G of x equals to integral from a up to x of t dt. Okay, let's see this one. Example 2. If g of x equals to integral from a up to x of t dt, where a equals to 1, and f of t equals to t raised by square. Is it t raised by square? Yeah. So find a formula for g of x and calculate g prime of x. Okay, let's see that. So g of x equals to lower limit is 1, upper limit is x. Now the integrand is t squared dt. Right? We can use the evaluation theorem. We said, okay, antiderivative of t squared. The integrand is t squared. Antiderivative, we get 1/3 of t cubed. Then evaluate at the upper limit, which is x. Subtract evaluation of 1. So at x, we get 1/3 of x cubed. At 1, we get 1/3. So in the end, we have x cubed minus 1 divided by 3. Right? So it's a function of g. And we call this function of g. Right? With this function, right, we can take a derivative of this function. So g prime. 1/3 of x cubed, that equals to x squared. Right? Derivative of negative 1/3, that's 0. So g prime of x equals to x squared. Or this x squared, let's compare this x squared with our integrand is t squared. Right? If we call this integral g of x, we see its derivative is exactly the integrand. Right? Its derivative is exactly its integrand. All right, so that's our theorem. So one part of fundamental theorem of calculus, very important. If f is continuous on a, b, right, x is in between of a to b, then the function g defined by g of x equals to integral of a up to x. X is the point in between of a and b, and the function f has to be continuous on this closed interval a to b. And also is an antiderivative of f, so which means f equals to g prime. Before we use capital letter F, right? We use capital letter F, but in this section they choose to use G. But if you want to make connection to be consistent with before with previous sections, you would think this G as capital letter F, right? Antiderivative. So the integral of f of t dt is f, and then the capital letter F prime is the integrand, right? So this is the first part of fundamental theorem of calculus. The picture is this. The picture is this. So the function f is continuous from the interval a to b, and the x is somewhere in between of a and b, and the area we can use g or we can use capital letter F to represent. All right. Okay, so if the condition exists, all right, if the condition satisfies, so g prime of x equals to f of x. Okay, the derivative of this function, it is the integrand. Also, we see from this example, right? We see from this example, g prime equals x squared. An integrand is t squared. Sometimes we would like to call this t dummy variables. It's just the variable changed, but the function is the same. T squared, x squared, the graph is the same. So the function is the same, just in different variables. All right, and also second one, right? Second condition, we have another condition is this, and the g and the f, of course, have to be differentiable, right? In the open interval from a to b. Okay, let's see this example. We want to find the derivative of the function, right? Which means we want to find the g prime. So we call the integral g of x. Right? So we want to find the derivative of the function. We want to find the g prime of x. Okay, that's our goal. According to this, right, we want to use this theorem. We want to use this theorem. We want to check, okay, if f is continuous on a to b and x is in between of a to b. So we want to find a certain b. To see x, f is continuous and x is in between of a to b. And then we could conclude g prime of x equals the integrand. Okay, the derivative of g is the integrand, of course, with the changing variable, right? So the integrand is a function in terms of t. Now we're writing it as f of x. Right? So g prime of x equals f of x. So let's check. Let's see. We have the function g of x equals the integral from 0 to x square root of 1 plus t squared dt. Well, square root of a function, then 1 plus t squared. So if we put into graph, is this the graph? No. So let's check. So part 1 of the fundamental theorem calculus gives g prime of x equals the square root of 1 plus x squared. Because why? Because it's satisfied, right? Well, what's the domain of this function, of this integrand? We have t squared, right? That means the domain of this integrand are real numbers. So we can talk about from 0 up to infinity. We can easily choose. So x is a number in between 0 and up to infinity, right? Because the domain of this function is all real numbers. So we can use the fundamental theorem of calculus to conclude g of x equals to square root of 1 plus x squared, right? And that's how we use the first part of fundamental theorem of calculus. Usually if we have something like this, right, and then we check, x is a value in between of a to b, just imagine a b, especially for these kind of functions, right? If the domain is everything, that's easy. If somewhere, we have a value is not in the domain, right, and is very close to the lower limit, we probably won't be able to make a conclusion. We probably won't be able to use the first part of fundamental theorem of calculus. Okay, let's see more examples. Let's see this one. Example 4 is saying, although a formula of form g of x equals the integral of this may seem like a strange way of defining a function, but books on physics, chemistry, and statistics are full of such functions. For instance, a Fresnel function is defined as s of x with integral from 0 to x sine of pi t squared over 2 dt. Okay, again, we have t squared here. So the domain of this function is all real numbers. It's all real numbers. Then we can conclude s prime of x equals the integrand, but substitute t into x. Okay, so just get used to this notation. Okay, so sometimes this notation is a little bit confusing for people. All right. Also, let's see here. Okay, so this one we can write it in another way. We can write it like a g prime of x, right? We take a derivative. We take a d dx, dg dx, so which is g prime. Then we take a derivative of this side too. We take a d dx. So that's this equation, right? So this equation is saying, okay, let's take a derivative on both sides. Take a derivative, so g prime of x, right? G prime of x. Let's start with g prime of x. So g prime of x. We take a derivative, so dg dx. Take a derivative on both sides. So dg dx, or g prime of x. We take it on the other side, same thing. We take a d of this dx. So differentiate, then integral anti-differentiate, right? It's like a plus minus, as if you didn't do anything. Because the derivative and antiderivative are opposite operations. So we take a derivative, so we integrate, then we differentiate. So that just gets back to f, gets back to the integrand, but with the changing of variable. So ft now change to be f of x. Right. So in the beginning, this is kind of confusing, but try to convince yourself, okay, to understand this notation. It's called, it's the first part of fundamental theorem of calculus. It's super important. All right. Right. So we use that. We take a derivative on both sides, or we just use the first part of fundamental theorem to conclude the derivative of s, just the integrand with the changing variable into x. Okay, let's see this example. So we want to find d dx. We differentiate, anti-differentiate. We apply we want to use this, right? We want to use this. But however, pay a very close attention. The upper limit here is x. We can use this. If this is not x, if this is 2x, 3x, or x squared, we have to do something else. All right, let's see. So this example, the upper limit is x raised by 4. Let me enlarge this. X raised by 4. So this is x raised by 4. So what are we going to do? Chain rule applied. So let's see how we do that. So we have to be careful to use a chain rule, right, in conjunction with part 1 of the fundamental theorem. So we use u substitution. We said, okay, let's call x raised by 4 u, right? Here I can call this f of u, right? I can call this g of u, right? I can call this u. The variable is just a variable. So temporarily, let's call this x raised by 4 u. So then d dx integral from 1 up to x raised by 4, the integrand secant t dt. We can rewrite it as a d dx integral 1 up to u secant t d dt. But here is u, here is x, right? It's not consistent. We have to keep the variable being consistent, which means we substitute x raised by 4 with u. We also have to substitute d dx into d du. So with the substitution, we want to find du. So what's du? Du is 4x cubed dx, right? If we think u, let's see, remember we call this a differential, right? Du differential of u. Or if this is confusing, thinking this way, we use, we make a temporary function, u of x equals x raised by 4. Right? Then we can talk about u prime or du dx. What's du dx? That's 4x cubed. Right? It's 4x cubed. Now let's multiply dx on both sides. Du equals to 4x cubed dx. Right? It's a different way of writing it, but it still comes from the understanding of this. So basically, we're treating u, the u substitution, we're treating u as a temporary function of x. Right? U of x equals x raised by 4. Then we want to find a derivative of u, so du dx, that's 4x cubed. Then we can multiply dx on both sides. So we can write a du equals to 4x raised by 3 dx. Now, given name of du, remember we call this a differential. Okay, differential. So usually when we use u substitution, right, we let u represent something in terms of x. Right away, we find the differential of u. So du, because we substitute into u, we also need to substitute the dx part, d dx. So u equals x raised by 4. That means du equals to 4x cubed dx. Right? So we want to substitute this d dx into d du. Okay, so what is the ddx now? So ddx, we want to multiply by 1. And this 1 is du times du. We want to multiply by 1. This, 1 is something divided by itself. Okay, and then we switch, because multiplication, we can reorder the order. We can rearrange the order. So we write a du times du dx. Let's put it here. Okay. So one way we use a u, substitute x term. All right. Another way we want to rewrite a ddx also. So we substitute x term. We also want to substitute ddx term. So ddx, we multiply by 1 to ddx. Then we rearrange the order. So we write a d divided by du, then du multiplied by du divided by dx. All right. So now we can rewrite this as a d du here multiplied by du dx. Okay, du dx. So if we multiply those two terms, right, du here is du divided by du still 1. We still get back to d dx. All right, so we know du dx, right? Du dx is just 4x cubed. So this first part, right, now we can apply fundamental theorem of calculus, the first part, right? We have from 1 up to u, secant t dt, right? Then du, right? Then we have d du. So this variable u. Now this part gives us a secant u, right? This part gives us a secant u. So secant u times du dx, and we know du dx. Du dx is 4x cubed. 4x cubed. So secant u is x raised by 4. So her secant x raised by 4 times 4x cubed. Usually we write 4x cubed up front. We leave the angle of the trig function the last term, so we don't get confused. All right, any questions for this? It could be very confusing in the very beginning. All right, let's see more example. All right, so this is a whole part of fundamental theorem of calculus. It's the first part plus the evaluation theorem, which we know already, because we have been using this for finding the definite integrals. So the first part of fundamental theorem calculus plus evaluation theorem now becomes the second part of fundamental theorem of calculus. So the condition is f is continuous on closed interval. Okay, closed on a continuous interval from a to b. So if g of x equals to this, right, from a, the lower limit is a, upper limit is x, ft dt, then the derivative equals the integrand with the substitute the variable. And the second part is evaluation theorem. See, the definite integral of f of x from a to b is its antiderivative. So f here means f prime equals to the integrand. Okay, equals the f. Its antiderivative evaluate at b, upper limit, subtract its antiderivative evaluated at a, the lower limit. Right. So this is the thing again, part 1 can be written in this case, all right? Or originally it read as g of x equals to this part, right? When we take derivative of that, that just equals to the integrand with substituting the variable. I think this is more important to understand this, or sure you understand this. because we use this very often in physics class. You know, you use this kind of function all the time. It's just a function, right? It's a function f of x. Let's read this. This is saying which says that if f is integrated and the result is then differentiated, we arrive back at the original function f. Okay? So you see f is the integrand, right? You integrated f, you know, on the ideal interval. You know, this we have this condition of this x on the ideal interval. Then you take derivative, right? Then you differentiate. Then you just get back to it. That means those two, under a nice situation, those two operations cancel each other. Part 2, right, is the same, like integral of a to b. You know, the integrand is someone's derivative. Then this whole thing is someone evaluated at b minus the function evaluated at a. Okay, so here we define something called the average value of the function on the interval. And then we can use this. So average value of function equals 1 over b minus a, upper limit minus lower limit, and integrate this, right? Integrate this, integration. All right, let's see example 6. Find the average value of the function. The function is defined on this on the interval -1 up to 2. So just apply this theorem, right? -1 is in the domain, 2 is in the domain, so you can use this definite integral. So 1 over 2 minus -1, that's 1 over 3. Then antiderivative of 1 plus x squared, that's x plus 1/3 of x cubed. Then evaluate at 2, subtract evaluation at -1. Then in the end, you'll get 2. You see the average value of the function equals to 2. Just a definition, okay? Maybe sometimes it's useful. Okay, the mean value theorem for integrals. Okay, if f is continuous on closed interval from a to b, then there exists a number c in between of a and b such that f of c equals to f of average value. All right, that's this. So this is the mean value theorem for integrals. Or we can rewrite this, so we multiply b minus a on both sides. That means the integral of this equals to b minus a times f at a certain value. But this example is to apply the mean value theorem for integrals. Yeah, we can get, so we did the answer, we have the answer already, right? So this is the same, we can write it as f of c is, you know, c is just a number in between of -1 and 2 multiplied by 3. So f of c equals to, so this side, right, we can evaluate, we get 2, right? We can go through this antiderivative process, we get 2. Oh no, hold on. Oh yes, right, because we multiply b minus a on the other side already. So let's see in the end, let's see, you know, f of c equals to 2. All right, let's do some exercise. So let this f is a function for the graph. All right, let's practice this. So first one, let's just practice this one. Let me just go through some, let's see. Okay, let's just do this one quickly. So we're given this function. We're given this function, right? Then let's evaluate g of 0, g of 1, g of 2, g of 3, g of 6. So I'm gonna do with you guys, all right? So g of 0, right? Substitute 0 into this. So then that means x is 0. Upper limit and lower limit equal to each other. That's just 0, right? So that means what's the area at this point? 0, right? A point does not have area mathematically. That's how we define so. Then g of 1. G of 1 is up to here. G of 1, right? G of 1. That means the area of this box. Right? That's 1 times 2, right? That's 2. Okay, then G of 2. G of 2, that means the area up to this. So we know G of 1 already. That's 2. And then also this down here is 2. And then here it's a rectangle. We have 1 times 2 divided by 2. Then add all together. Then G of 4 is the area up to this. Oops. Right? So we find the area on the top of x-axis, then subtract this little rectangle here. G of 6 is up to here. So we need to find the area up to this. The upper part will be positive. Up, upper means above t-x-axis. Down below t-x-axis will be negative. We'll do subtraction. All right. Okay. I don't want you to do this. Let's try here. Okay, let's try 5. Let's try 5. 8. 8 is a special one. I want you to think. Okay, let's try 5, 6, 7, 9, and 10. All right, let's try this 5. And this 5, we use the first part. All right. Okay, try this 5 now. Okay, if anyone like to show, type the number in the chat. If you have any questions, yeah, ask. We are approaching to the end of the semester, and we have a lot of people being absent, not presenting. I really worry about these students. Okay, anyway. Okay, anybody like to show? So 5, 6, 7, 9, 10.
Professor?
Yeah.
Can I just say 5? It's simple, so I'll just explain it.
Oh, sure.
Okay, so for 5, we're going to take the antiderivative of the function 1 over t to the third plus 1 is f of x, right?
You're asking me or you're presenting?
So basically, g prime of x would be 1 over x cubed plus 1.
Okay, so why?
Because we're going to take the antiderivative of 1 over t cubed plus 1. And
how would you take an antiderivative? Which one tells you can take an antiderivative? Which theorem back you up about that?
Oh, okay. So the first part theorem of the fundamental theorem of calculus, the first part.
The first part.
It says that f of x equals the antiderivative of f of t dt. F of t is 1 over t cubed plus 1.
Okay. So why? So what? Right. What? So what kind of condition satisfies for you to do that, to apply first part of fundamental theorem of calculus?
Can you repeat that? I didn't hear it.
I said, right. You are applying the first part of fundamental theorem of calculus, which is right. I'm asking you, right, because to be able to apply fundamental theorem of calculus, you have to satisfy the conditions in the theorem. So what is the condition you have to satisfy here to apply the theorem?
Oh, okay. Professor, can you hear me?
Yeah, I can hear you now.
Oh, okay. So I'm a little bit confused on that, but what I think is because of the interval x and 1.
Right, that's not an interval, right? Okay. All right, let's see if maybe you see Amir typed for you, saying the f of t is continuous in the interval on a and b, a to b. So can you find the interval for such x? Because first we may not be able to apply antiderivative, right? You know why we cannot? We know how to, right? If you give me a definite integral, which means we have a lower limit, we have an upper limit, and we can do that. We can antiderivative the integral. And if you give me indefinite integral, I also can apply antiderivative. But here we have a lower limit being a number, upper limit being x, being a variable. We don't have any tool to do antiderivative, right?
Yes.
Right. So that's why I said when you say do antiderivative, I ask you which rule back you up with that. No, we don't have any rule to back us up to do with the lower limit being a number, upper limit being a variable. But right, you said we can apply fundamental theorem of calculus, the first part. But to be able to use the first part, it has to satisfy certain conditions. Okay, let's see. Anyone wants to try to explain? Okay, let's hold on this. Let's hold on this. Ursa, you just listen to it, all right? Because I don't want to tell you the condition yet. Which when I talk about examples, I emphasized on it. Probably you missed it. All right, let's see. I think Emily wants to try 7. Yeah, Emily, go ahead. Explain 7 to us. Yeah.
Maybe I have the same issue as Ursa, but can I still try question 7?
Yeah, you can try 7.
Okay, so first I looked at the function t minus t squared to the 8th power. I see that it's continuous because the domain is all real numbers, so it satisfies the integral from 5 to s. And then according to part 1 of the theorem, we know that g of s is equal to the antiderivative of f of x. So when we find a derivative of g of s, it cancels out with the antiderivative. So in this case, the answer is g prime s is equal to s minus s squared to the 8th power.
Okay, great, Emily. Ursa, did you hear Emily's explanation?
Yes, but I'm still confused on the part.
Okay, let's keep trying. No, let's just wait. All right, Emily, good. Thank you. Let's see, anybody? Okay, 6. Zuli wants to try 6. Zuli, go ahead.
Yeah, so for the part 1 of the fundamental theorem of calculus is d over dx from the integral of a to x of f of t dt equals f of x. And so if you apply that to question 6, where it's g of x equals 1, the integral of 1 to x of 2 plus t to the 5th power of dt, you would just get g prime of x equals 2 plus x to the 4th to the 5th power.
Okay, you're missing one very important. So what's the guarantee you can do that?
It's continuous. Or it's a continuous function.
On what?
On the wait, sorry. What do you mean continuous on what?
Because usually you cannot just see f is continuous. F is continuous on what? Domain.
From the integral to 1 to infinity.
Right, okay, you could see, right, the function, right, the f of t is continuous on all real numbers.
Okay.
Okay, I see. All right, okay, good, Julie. Now, Ursa, did you see the point?
Is it because you have to find that it's continuous on which intervals?
Right, because the condition in the theorem is f of t. Your f of t is 1 over t cubed plus 1. Has to be continuous in the interval from a to b. Okay, can you tell us what is the domain of f of t here for 5?
Oh, okay.
So can you tell us the domain of your f of t?
Is it from 1, it's all real numbers? Like 1 and above?
No, okay. Let's say f of t equals 1 over t cubed plus 1, right? Can you tell me the domain of this function? Don't think about anything else. This is a pre-calculus concept. Domain of a function. What kind of value of t can work with the function? Or let's ask you this. What kind of value of t will cause the denominator to be 0?
-1.
-1. Perfect. So, can -1 be in your domain, in your interval from 1 up to x?
No.
No. So you're safe, right? So you just see, okay, the domain of this function is a negative, cannot be -1. But my interval is from 1 up to x, because x is greater than 1. So it's safe to apply fundamental theorem of calculus, part 1. Does that make sense?
Wait, can you repeat what you said?
Okay. You just said the domain of this function is every real number but a -1.
Yes.
So -1 is not in your interval from 1 up to x.
Yes.
So it's safe. So because from 1 up to infinity, this function is continuous. So x can be any value in between.
Okay. I get it.
So that's why you can apply fundamental theorem of calculus part 1.
Okay.
All right, great. We're learning it together. You're welcome. Okay, anybody else like to? So we have 5, 6, 7. Okay, great. Noella's 10. Okay, explain to us, Noella.
Hello?
Yeah.
Hello?
Yeah.
Okay, so for this question, I used the same method and the same tactics that one of the previous questions used in the previous pages. So I set it equal to d over dx times the integral from 0 to x squared, radical 1 plus r cubed times dr. And then I set u equal to x squared, and from there I substituted u. And then I did d over du times the integral from 0 to u, radical 1 plus r cubed times d over dx. And using the chain rule, I simplified it further and I substituted u as r. So I got radical 1 plus u cubed times du over dx. And then from there, I substituted x squared as u and multiplied it by the derivative of u itself. And then as the solution, I got the derivative of h of x equals to 2x times radical 1 plus x to the 6th power.
Okay, great. Let me ask you this. All right. So you are applying fundamental theorem of calculus.
Yes.
Can you tell us, like, what kind of condition you satisfied to apply that?
We applied part 1, which means that f satisfies, or the function satisfies, because the function itself is continuous on a closed interval from a to b.
From which a? But what is a? What is b?
So 0 to x cubed.
0 up to positive infinity, right?
Yes.
Yeah. So, right. Okay. All right. Good.
Thank you.
Okay. Thank you, Noella. And anybody else? So we have one more question, right? We have 9. Anybody likes to show 9? Anybody has a question with 10? Beautiful work. Okay, Amir, let's do 9. Go ahead, Amir. Oh, all right.
All right, Professor. So for 9, we're given the following. We're given what do you call it? We're
H of
given
x equals to
1 second. Let me just look at it.
mm,
So we're given h of x. Yeah. All right. That's equal to what? The integral where we have 1 over x2. And then our function is sine to the 4th power t, and then dt. Yeah. So first of all, what I did first was so first I rewrote this. So this right over here, you can rewrite this as the derivative of so ddx, and then you would have here you'd have your 1 over x 2, and then you'd have here the same thing. That's what we're trying to find here. So from then we could set u equal to 1 over x. We know it's continuous. And then from here we're gonna have to find u prime eventually. So we know this right over here, this is x to the negative 1. The derivative of this is negative 1 over x squared. So from here we can rewrite this expression as the derivative of u. And then we have here in brackets our original thing. u1. Yeah, so we basically have u, which is our 1 over x, and 2. Sorry. Then we have here sine to the 4th power t dt. And then we have that, and then we have the derivative of u with respect to x, so du dx. And then finally we can simplify all of this to just so that would be the sine to the 4th power of u, which is just so f of u, that would be sine to the 4th power of 1 over x, and then we would multiply that by our derivative, which is negative 1 over x squared, and our final answer would be, 1 second, negative sine to the 4th power 1 over x squared. Oh, that's it.
so what is your answer is what? You cannot be equal to h of x, right? What's your answer? You probably want to use another.
Do you mean h prime, or do you mean?
That's right. That's right. Maybe start from here.
Oh yes, I have trouble I have to
Yeah.
rewrite them each time.
Yeah, maybe start from the second line.
Yeah.
H prime of x equals to.
Yeah, I just
dd.
drew an arrow just to save time.
I see. So this equals to, in the end, equals to that. Okay, great. Anybody has any questions? So this is a bigger part, all right? So this is a bigger part of this fundamental theorem of calculus, the first one. And also, I'd like to ask you the same question. So you're applying fundamental theorem of calculus. So why the condition is satisfied?
Okay, so we know that for this one we're given sine to the fourth power t. So well, to apply it we have to know that it's continuous on an interval a b. So from 2 to 1 over x, we could say it's continuous.
Why it's continuous?
Um,
What is the domain of a sine function?
so the domain of the sine function, that would be sine function is all real numbers. This is sine to the fourth power though.
Right. Sine is all real numbers. So sine to the fourth will change the domain.
Well, when I look at the graph of sine to the fourth, I'm not really seeing that much. Like,
Well, you can think about that. Okay, that's a very good question.
because I have a graphing calculator. That's why.
I see. Okay, let's see. F of x equals sine x. So we know the domain is all real numbers. So if we put a root on this, if we say, okay, put a power on this. If I raise f of x, the fourth power.
Well,
Right?
for 1 over x, x could be either negative or positive. That's what. Yeah. Right?
Right. It's still all real numbers, right?
Yes.
The power wouldn't change the domain in this case. Okay. So right, that's right. So sine function, the domain of sine is all real numbers. And this interval here, the lower limit is 2. So 2 up to infinity. Sine is continuous.
Well, I understand because 1 over x can only be undefined for 0, and 0 isn't in the domain from 2.
We don't really consider 1 over x though.
Oh, okay.
Yeah, we only consider the integrand.
All right.
Okay, good. Thank you. Anybody has any question? Let's see if we. Usually it's right. It's very easy for students to stumble on this. Okay, let me leave some you can practice for next class. So maybe try those 3. Try 11, 12, 13, and maybe 14 too. All right, and let's see down here. Find the average value. Okay, I'll just leave this. I'll just leave this 4, okay, for you to practice. Oh, you cannot see it? Oh, okay. I'm not sharing my screen with you. Sorry. Okay. So, right. So try this. Okay. We'll review these 4 questions. So next class, so 11, 12, 13, 14. Okay. Anybody has any questions? If not, I'm gonna go for new material, all right? Okay, 4.5, substitution rule. Okay, stop me anytime when you have a question, all right? Substitution, we already used the substitution rule for, right? We see Noella and Amir showed us to use substitution rule. So let's talk more about that. Let's see, if we want to find out this indefinite integral, right? Indefinite integral, we can enter derivative of the integrand. So how would we do that? So for this one, for the simple one, we're able to apply power rule. We're able to apply trig rules. But what about with this? You see, we see this integrand is a product of two functions, right? So basically, so let's call this f prime. So f prime of x equals 2x square root of 1 plus x squared. To do antiderivative, we won't be able to apply power rule because it's not only one term. It's not one term. It has two. It has two. It's a product of two functions. And we have 2x. It's not a simple. It's not. We cannot apply a power rule for antiderivative, right? So what do we do? So what? So we okay. How do we find f of x? One way we could, make a guess. We could think, okay, I can think whose derivative is that, right? I may think that might be square root. So I can rewrite this as this something raised by half, right? We can guess and check. We can guess and check. It's one way to do it. Just check, okay, just make up an f, then go from there, right? To see whose derivative to differentiate the f. Then to see which one is 2x square root of 1 plus x squared. But another way is to use substitution. We see, okay, I have 2x, I have square root of 1 plus x squared. Maybe I'll use u substitution, especially we call u substitution. Let's see. So we let u, we let u be 1 plus x squared, be under the square root. So let u substitute 1 plus x squared. Then right away we figure out du. Then du equals 2x dx. Right? Again, we're looking at u as a function of x. Right? Then u prime or du dx, that's just 2x. We multiply 2x on both sides. We can write differential of u as du equals 2x dx. So this means we want to substitute x in terms of u. At the same time, if we do that, simultaneously, we have to substitute dx into du. Does that make sense? All right, we can substitute one variable, but then simultaneously, we'll have to find out the differential of the variable. So we made a relation in between u and x. And simultaneously, we have to make a relation of the changing in u and changing in x. Because we need to substitute x term into u and also this dx. Right? We need to change both notations. If we want to represent the x term in u, we also need to substitute dx into du. So we let u be 1 plus x squared. So rather we figure out du dx as 2x, or we rewrite as du equals 2x dx. 2x dx, we check right here, right? We have 2x dx. Here we have 2x, and then we have dx. So 2x dx, we're going to rewrite as du, right? And square root of 1 plus x squared becomes square root of u. So we rewrite this term. So this 2x dx becomes du. Square root of 1 plus x squared just becomes square root of u. Now we can apply power rule for antiderivatives, right? U to the half. Now we add 1 to the half, get 3 halves. We divide by 3 halves, that's same to multiply by 2/3. Then plus c, because it's an indefinite integral. So we add a constant term to it. Then we rewrite. So 2/3, or u rewrite as x squared plus 1, raised by 3 halves plus c. So that's to use u substitution. Okay, the trick is this. We rewrite x into u term, and we rewrite dx into du term. All right, if we remember this process, so we need to find the u, we need to find du. U in terms of x, du in terms of dx. Then we substitute the x term into u, the dx term into du. Okay, let's try more examples. Well, of course, if you take a derivative, we'll get back to the integrand, right? So why we use u substitution? Basically, that's from chain rule. If we have composition of functions, chain rule applied. So we see this, right? This is composition. This is the functions of a composition of functions, right? We see the outside layer is a 3 half. The inside is x squared plus 1. So with composition of functions, we get the term with product of functions. So we won't be able to apply power rule. So that's why we need to use u substitution. Okay, let's see more examples. So it's this, right? So we want to rewrite. Think about this as like a f of x dx term. We want to, well, let's think about this as, this is the inside, the integrand with the dx. Then we have f of g of x times g prime of x, right? Look at this. This is our f of g of x, right? This is g prime, then dx. So we want to rewrite it as in fu du term. Well, let's see this one. This one we want to use, so we have x cubed cosine x raised by 4 plus 2. You see this is a gx, right? And the x cubed is part of the g prime, But anyway, so let's use u substitute x raised by 4 plus 2. So with this composition, right? This is composition of functions. So we write u equals x raised by 4 plus 2. Right away we figure out du. So du equals to 4x cubed dx. So now let's do a substitution. So we substitute x raised by 4 plus 2 into u. So we write cosine x raised by 4 plus 2 into cosine u. Now we need to figure out the rest. So du equals to 4x cubed dx. We check the integrand. The integrand we have x cubed, we have dx. What's missing? We're missing this 4, right? We're missing this 4. So let's divide by 4 on both sides. Then we get x cubed dx equals to du divided by 4. Right? So we substitute x cubed dx into du divided by 4. Du divided by 4. So now the 1/4 we can pull out, right? So 1/4 of integrate cosine u du. Nice. We know how to antiderivative of cosine u, right? that comes from the antiderivative of cosine u is sine u. So quarter sine u plus c. And u, we read back in term of x. U equals x raised by 4 plus 2. So we get a quarter sine x raised by 4 plus 2. Then add the constant term c to it. Any questions? All right, so basically, in the integral, we're trying to find f of g. F of g. We try to find composition of functions. Right? In this case, we see f is a cosine, g is x raised by 4 plus 2. Right? And this is a part of g prime. Right? G prime is 4x cubed. We're missing 4 there. We're missing 4, so when we anti-differentiate, we compensate with 1/4. Right? Usually, when we do substitution, we let the g be u. Okay, once we figure out f of g, so we let u substitute the g part. So this is what people call u substitution. Okay, let's see more examples. So in this case, we have a square root of 2x plus 1. We see f prime of g, right? We see f of g, not f prime of g. We see f of g. So what's g? What's f? F of x. You don't really have to do this, but you know, this will be helpful. So root of x. What's g? G of x equals to 2x plus 1. So one way to think is you can think this way. You can think this way. Then you said, okay, let u substitute the g of x. So equals to 2x plus 1. Then right away we figure out du. Du equals to 2 dx. So we rewrite as dx equals a half of du. Right? Then now let's substitute. Substitute square root of 2x plus 1 into square root of u, and dx into half of du. We factor out a half, so u raised by half. We know exactly how to antiderivative of that, power rule. Then we get 1/3 of u raised by 3/2 plus c. Then we rewrite back the x term for u. So this is the antiderivative, this indefinite integral. All right. Let's see example 3. Example 3, we have x divided by square root of 1 minus 4x squared. So let u substitute 1 minus 4x squared. Then let's figure out du. Du equals to negative ax dx. Well, now we check the integral. The integral we have x dx, right? So let's rewrite, let's divide it by negative a on both sides. So x dx equals to negative 1/8 du. Now let's substitute. Okay, we'll have du term, we'll have u term, let's substitute. So negative 1/8 factor out the integration of 1 over square root of u du. When 1 over square root of u, we can rewrite as u raised by negative half. And we know how to anti-differentiate that. Add 1 to it, divided by the new exponents. Then in the end, we get negative quarter square root of u plus c. Substitute back the x term into u. So that's the answer. Any questions? Okay, let's keep going. So this integral is cosine 5x, right? So let's use substitute 5x. So we see this is g, f of g, right? 5x, then du equals to 5 dx, or dx equals to 1/5 of du. Now we're ready to substitute. So we substitute cosine 5x dx into 1/5 of cosine u du. And we know, so u du, right? We know how to anti-differentiate cosine u. That's sine u. Then we write back into x term. So 1/5 sine 5x plus c. Well, let's see this one. Oh, this one we already did. Okay, let's see definite integrals. Right. Definite integrals. Here we have square root of 2x plus 1. We anti-differentiate, we use u substitution. When anti-differentiate, that's one of the examples before. We get 1/3 of 2x plus 1 raised by 3/2. Now we want to evaluate at 0, at 4. So evaluate at 4, then subtract the evaluation at 0. Evaluation at 0, this time 0 is just 1, right? Evaluation at 4, 2 times 4, that's 8. 8 plus 1, that's 9. So 9 raised by 3/2, right? 9 we can write as 3 squared. So 3 squared, then raised by 3/2, that's a 3 raised by 3, which is 27. 27 minus 1, 26. Okay, and then we get 26 over 3. So definitely integral, right? So this is the same, right? We get, so changing of limits. Usually, sometimes people like to change the limits. So here, right, with the variable x, the lower limit is a, the upper limit is b. And then when we change it into u, one way is we can change the lower limit and the upper limit. So we change a into g of a because we think about this f of g. And the upper limit is g of b, but we don't have to do that, okay? We don't have to do this. We don't have to use this. Why? Because we can always substitute back into x. We don't want to evaluate when it's u. We want to evaluate it when it's x. But if you don't want to substitute u back into x, you could change your lower limit, you could change your upper limit. Just another way of doing it. Okay, let's see example 5. So we have dx over 3 minus 5x squared. So let's rewrite 3 minus 5x into u. So u equals 3 minus 5x. Then du equals negative 5 dx. So now let's substitute. So dx equals negative 1/5 of du, and this bottom we can write as u squared. So we have du u squared. So one way we could change the limit, or we don't have to change the limit, right? So we anti-differentiate 1 over u squared, we get negative 1 over u. We can substitute this u back, because u is 3 minus 5x. We just write it as negative 1 over 3 minus 5x. Then we can still evaluate at 1 and at 2, then subtract them. Or if we don't want to do that, if we want to change the limits, because we change the variable, so also we want to change the limits. So what do? We just rewrite them, right? If x equals 2, because we let u be 3 minus 5x. If x equals 1, right? If x equals 1, so u equals to 3 minus 5 times 1, we get negative 2. So we change the lower limit in terms of u to be negative 2. The upper limit is x equals 2. If x equals 2, we substitute into u, we get a u equals 3 minus 5 times 2. That's negative 7. So upper limit becomes negative 7. You see, this is a little bit weird, right? Because the lower limit is bigger than the upper limit, right? But doesn't matter. This is pure mathematics, all right? If we switch, we can switch the lower limit and the upper limit. That will introduce a negative sign. But for definite integral, it's okay. For definite integral, it's okay, all right? So we just substitute, in this case, we just substitute u, keep u. We don't have to switch back to x term. So we evaluate u at negative 7, we evaluate u at negative 2. Then we get this. So if you don't do that, if we keep as x term, we will get a negative, well, negative times negative will be positive, right? So we get a 1/5 of 1 over 3 minus 5x. Right? We can keep like this. Oops. So this, I have another Then we can evaluate at 1, at 2. All right, we'll get the same exact answer. So you have choice here, all right? Okay, so this is something about even function and odd function. Well, let's see, what is this? So if f is continuous on negative a to a, right? So the values, the absolute value are the same. You can think like this, right? Negative a is on this side, then up to a is on this side, right? So this is negative 8, this is 8. If we want to evaluate some area of under this function, it depends on this function, right? Depends on what kind of function is this. Imagine if it's odd function, right? Let's say x cubed. Oops, it's not exact, right? Think about an even function, x squared. What happens? Right? Think about the area. Right? X squared is an even function, right? X squared is an even function. If we want to evaluate from negative, let's say negative 1 up to 1, we see the area we can evaluate this from 0 to 1, then double this, because this area, the same. Because even function, we can just double it. We can just find a function from 0. We just find the integration from 0 to 1, then double it. So that's what is saying here. If f is an even function, then even function means this, f of negative x equals f of x. Then from negative a up to a, integration from negative a up to a, f of x dx equals 2 times the integration from 0 up to a, right? So one example to remember is this x squared, because x squared is an even function. But now let's think about an odd function, right? Odd function, let's use x cubed, or even 1 over x, all right? But let's use x cubed. So x cubed with something like this. I have to do 2 of them. It's not exact, I'm sorry, right? So if we want to find the function, the area from here, roughly from here to up, so this is a negative a, this is a, you know, x cubed function is symmetric to the origin. So we see the absolute value of the area of this part equals to this part. But one is above x-axis, one is down below x-axis. So the area of this is negative. So they cancel each other. So that equals to 0. So let's see. This example is for f of x equals to x cubed. So that's for b, right? If f is odd function, f of negative x equals to negative f of x, that's the definition of odd function. Then the integration from negative a to a equals to 0, right? So if the integrand is even, it's from negative a up to a, the area is double the half. If the integrand is odd, no, if the integrand is odd function, and the integral is from negative a up to a is 0. The two areas cancel each other. All right. So that's a picture proof. Okay, any questions? Let's see. Oh, I'm sorry. I went over time. All right. No, okay, maybe I'll give you some. Sorry, time passed really fast. Sorry. Yeah, try this. Try those functions. Let's evaluate the indefinite. Let me choose a couple of them. Yeah, let's try this 4. All right, for next class. Thank you. Yeah, always remind me, always forget something. Okay, thank you very much. So see you next class.